for a solar model, for a solar radiation model. Oh, I lost it. Okay, I got lost. Sometimes you get lost. Anyways, so I want to now print the last info report for all of them. I also want to compute the point density, and that's something new I want to teach you because it's useful sometimes. I want to create a small histogram. I want to create a histogram of the Z values, because you know the Z values seem to be going a bit crazy for a few points. So I want to create a histogram of Z values. For every 10 meters, I'm going to create a histogram. So I'm slicing the Z domain into 10-meter intervals, and I count how many fall into every 10 meters. And as you can imagine, there'll be some areas where the ground is where I have lots of points, and then as I get up to 400 meters, there may be only one point in that interval. Just sort of to get an idea where the noise is. That can be useful. And I want to teach you the functionality of a histogram computation. You can compute a histogram for many different things. Scan angles, and so on. And again, you have to press add in order to actually show up there. And I also want to, I haven't done that yet. I want to create a quality folder where I can put all these reports. So I'm going now back to my folder where the Argano dataset is in. I'm going into the 1 kilometer folder, and I created just inside there. Quality. So I created inside of the Argano 1 kilometer. Now I go back to my remember to unclick selected file only, so we have all files. I'm running on all cores. And the output option, there's two ways of doing it. The easiest way is just to go here and pick this. The *_info.txt. That's the one we took last time. And I say run. And again, if you just missed one option, you can always type it now. So we have our files. These should all be the flight lines from Argano. This is the names, the strange names you see here. Those are the names that are coming out of the LMS system, the system that produces them by using the raw scanner data files and the trajectory files and all these sensor files that are collected during the flight, and then produces the final XYZ coordinates. So everything looks familiar. Oh, we haven't picked the output directory. We haven't picked the output directory. So I say cancel, and I go to output, and I pick the output directory. Quality is use current. That's why it's always good to check the command line. So the CD Go ahead, let's go through it. So now I have the output directory, minus CD, minus compute density. You can actually write compute density also, but because I often type this, minus CD is a lot faster to type than minus compute density. And this is a new command that we didn't have before. Minus histo means compute a histogram of the Z values and compute it for every 10 in boxes or in bins of 10, in intervals of 10. Okay, I think that looks good. So I started. And it's done. Now before you exit the program, I would like you to compute a second kind of report that doesn't have a GUI. That's a fairly new tool I developed in order to validate files if they are spec conform. They're conforming with the specification of the file format. I did that originally for the ASBRS contract, but then the contract fell through and well, and I don't have a GUI. And if you don't follow this exactly like I do and it fails, it's no big deal. I just want to show you that this exists. There's a program called LASValidate. Now LASValidate does not validate the correctness of your LiDAR. LASValidate validates the correctness of your file. The points could be complete garbage, but they could be correctly formatted and they would be fine. So I think we need to get rid of the cores because it can only run on one core. It doesn't know anything like ODX. We need to get rid of all of this. And I'm not sure I think the ODX command might exist. Ah, damn, I should have tried it out before. Oh, but we can make one report. So what you can now do, I often go in here and I play with this, and this is sort of an easy way of starting to work with the command line. You just modify the command you see here, which is basically the same as writing it in the command line, except it already writes something for you. And you don't have to open that black window. So I'm deleting the dir, so it just says -O, so I give it as an output file. And LASValidate produces XML, because XML is a nice ASCII output for parsing, and I'm producing right here sort of validate report .xml, or maybe validation report. Sounds better. So this will now take all these files and produce one report which says if these files are specification conform. That has nothing to do with the quality of the LiDAR. And I hope this would work. I never really tried this in a workshop setting like this. So, doi. That's a good sign. So there's no multi-core. It's just a very simple tool. It's written to be very, very simple. The source code is available. It's an open source tool. It compiles on every platform, and that's why I don't have multi-core support, because multi-core support is a bit different on different platforms. Okay. Now we can exit LASinfo and look at what we created. Here's a quality report folder, and inside first of all the info reports. Let's have a look at those. We know that already. It tells us first which file it was, and then usually if we had gotten the raw data, raw, it would say something about Optec LMS here. But I told you, Charm cut out 1 kilometer slice from these strips. And whenever a software operates on a file, it usually overrides who is dealing with the software. And in this case, it looks to me Charm hasn't updated her LAStools since April 15th. It's about time. April 15th, that's 3 months old. So I told you before, point data format in Dream is usually 1. These are 28 bytes. It's the extra 8 bytes for the timestamp. Here we have the bounding box, and you see we go from 63 meter to 400 meters. So the 400 meter, that's mostly the noise points. And here's one of those variable length records that I talked before. A variable length record. It has only one, and it's called, and this is one from the specification, it's a projection record. And that specifies the projection information. Sometimes it's wrong, but this one seems to be correct because LASinfo doesn't complain that it doesn't know anything about it. And somewhere it should say, yeah. So this is the important one. This is called an EPSG code, and it specifies all the different projections in the whole world. And this one is, the particular one is a UTM. U1 is where we are. Here's our minimum and maximum. For some strange reason, all the user data values are 255. I don't know why. You know why? It appears, I told you before, the user data you can really put whatever you want, but usually a good software, when they output the final result, especially like a processing software like Optec, it's only one value in there, 255. I would put zeros there, not 255. Just seems clear. You see the scan angle? It goes from -22 to 23 degrees. That's the scan angle of the scanner when it goes left, right. That's the scan. Did that make a good impression of the scanner? It's more like a grandfather clock. See? Oh. And here's our histogram. So between 60 and 70 meters, we have 1.6 million points. Between 70 and 80 meters, we have this many points. 80 and 90, we have this many. And you very quickly see that when the noise probably starts, right? I mean, I would say these are probably definitely annoying. Definitely from here, because there's almost no points. You know this notation, right? This means 90 is not included. So it goes to like from 80 to 89.999999. It's a mathematical interval notation. Okay, and here we have the average point density, 2.36. That's an average. And there's no warnings anywhere. It doesn't say that's not good, so it looks good. Let's have a look at this other file that I created, the last validate one. Just so we didn't. It's right here, it's an XML file, so if you have a browser that knows how to read XML files, for me it automatically opens the Explorer, and basically the last validator has all these reports. For every file, it creates one report and a summary. Pass. That's the best grade we can get. Pass means everything was okay. It has a CRS, that means Coordinate Reference System. So pass, that's good. It's also pass. Wow, that's like a grade A student. Pass, 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 pass. You go to the bottom, and here's the total. We have 9 pass, 0 warnings, 0 fails. Perfect. Very good data. From a pure specification point of view, these files are following the ASBRS guidance in all details. And it also saves the command line here that was used, so you know how it is generated. We didn't have, when you got the training 2 years ago, this tool didn't exist. But okay, next thing, let's make a LAS boundary. Again, I'm browsing through my files, sample data, Agno, 1 kilometer, add them all. And instead of making a lot of individual boundaries, this time let's make only one boundary. And remember, for one boundary, we can merge all files into one. And we're going to do one additional step here. We use a concavity of 50. That means, which concavity do you use? 10. That means if there's a hole of 20 meters in the data, we will not notice it because we only find things that are 50 meters or bigger. So in the DREAM project for the quality reports, they use a concavity of 10. So if there's anything of size 10 or bigger, it will appear. So this means smaller holes will already be reported, and the boundary will be a bit more precise, because the triangle monster can eat deeper into the concavities. We also show the holes and make it disjoint. We can output a KML file because we have projection information. Now this is not too much data, but sometimes you have a lot of data. And even LAS boundary is very scalable, it's too much data. What we can do then is we can help LAS boundary by throw away a few points in the first place. And we can do that with a filter. And there's one filter we haven't used yet. It's under by various criteria. This filter is called thin with grid. Thin with grid, it puts a grid over the points and only lets through the first one that falls into every grid cell. All the other ones are getting deleted. But for making the boundary, that's not such a big of an issue because, you know, we don't really need to know all the points, we just need to know where the points are. And, yeah. Which value do you use for thin for grid? You use 2. So, Char puts over the entire area a grid with 2 meter spacing, 2 meter by 2 meter. And of all of them, she only takes 1 point. That will significantly lower the number of points, because we have about 2.3 points per square meter for one strip. If you now put them on top, we get up to 4 or 5. And 4 of those would be up to 20. And for these 20 points, we only keep 1. So it means the number of points that last boundary has to process will be significantly lower. And that can sometimes allow you to process really large areas, which otherwise would cause last boundary to be out of memory, because it's 20 points to process. So let's do this. Let's put a value of 2. So this value should be lower than the concavity, obviously. And maybe 5 times lower. Concavity of 10, grid of 2 is a reasonable thing to choose. Don't forget to add it. And finally, we want to select the output directory, which is the quality directory. And we want to give it a nice name, like boundary. What do you call it usually? Charm, what do you usually call it? This file. What do you? Oh, you call it Agno boundary? Okay. There we go. And I think that's it. So let's see how the command line looks like. Right. So last boundary, list of files is to make sure we have the right ones in here. All the Agno files. We will merge them into one. If you don't have that, you would do that for every strip individually. Then we are thinning them with a grid. So we merge them and then we thin them. We tell the monster to stop eating when the triangles reach an edge length of 10 or smaller. We look for holes in the middle and we allow the polygons to become disjoint. And we put the result into this directory and give it this name. KML, remember KML only works when you have projection information. I'm not sure I checked for it. I think I give you a warning if you don't. And I say start. It's often good to check this black window, because if there is something you're doing wrong, it will be reported here. That's where the error messages or the warning messages will appear. So in this case, no warning, no error. Looks good. So let's see what we did. There's Agno boundary, and I'm double clicking it, and I think I'm still online, yes. And oh, I'm leaving the USA and I'm going to Agno. I had no idea where Agno was. Here it is. Which island are we on? Oh, it's Luzon Island. It's much more fun now, right, than in the Philippines. Because it's more fun in the Philippines. So what do we see here? Well, we see some areas, some holes in the middle of the data. This looks like a river. We see that joke before, you know. These returns never came back. They're still like swimming in the water there, like, hey, had a drama here. Here, I would assume some other kind of water. Maybe fish ponds. When it's aligned to some structures on the ground like this, it's usually water areas. Now, if here in the middle of the field would be the big thing missing, yeah, it all looks like water areas, I think. Because the Dream Team also collects auto photos, you could actually go in and check if there's any suspicious area where you think data may have been missed. But also, if there's data missing, we can also see that later in the density and the overlap images, which we are going to generate next. Okay, so that looks pretty good. Let's go to last overlap. Do I still have to say everything, or you already know what to do now? Last overlap. To the sample data. Agano, 1 kilometer. Load them all. Set the output directory. We go into the quality directory again. Use current. Give it a file name. Let's call it Agno overlap .png. Yeah. So usually this will be a block of data that has like a unique number, like Agno 7b, for example. Because Agno, that's definitely not Agno. Agno is much more. So this is just for the exercise. We don't know which block it is right now. Or I don't know. But files and guidelines. That's correct. And which pixel size do you usually use? 5? One? One may be not enough because we have low density. I think 5 is because our density is only 2 points per square meter. So you use 1, we often don't have 1, and what we get. If you set it too low, then you often get very poor images because there are empty pixels everywhere, and that is not a. I think 2 is sort of the minimum for. But if you have really big data, then you may consider setting it to something higher, like 5. But what about the maximum difference value? 0.25, because we want to see where the data is more than 25 centimeters difference between the flight lines. We want it to become red or blue, depending which way it goes. And I think this is it. Yes. So let's say run. And let's see if the command line makes sense. List the files, merge files of flight lines. The maximum difference is 25 centimeters. Should elevation lowest, the output directory, and the output name. Looks good to me? So I say start. Who is curious what we just created? I am. I haven't seen this data before. So Agno quality see there should be now Agno overlap and Agno diff. So I'll double click those and add them to our visualization here.